Hello, folks. This is Mr. Walker here, coming to you with our notes for Intro to Proofs Part 1. Now, this is going to be a review of algebraic proofs as well as talking about the building blocks that we're going to be using for our geometric proofs in the future. So, let's just go through and recap what do we know a proof is. So, a proof in geometry is the process of making claims and providing evidence to support each claim until we reach our conclusion. We use them to verify the truth of a statement. Just like a lawyer fits pieces of evidence to build their argument, so do we with geometric proofs, geometry proofs, even with algebra proofs. Now, writing a proof is like completing a puzzle. You begin with your given information and we work to reach the goal statement, what we're trying to prove. You will make a series of related claims and back each one up with justification until you complete the puzzle. We're not going to be going through and taking our best guess with these things. There are things that we can go through to work to our eventual goal, but we have to be deliberate with making sure this makes sense. We're going to be using our deductive reasoning skills, our definitions, our postulates, and our theorems to go through and jump into some stuff. So let's talk about the baseline things that we talked about from our previous use of proofs back all the way at the beginning of the year. So these are all our different properties of equality. These just let us know how we solve our equations and what steps do we know that keep things still equal. So when we're dealing with our operations like addition, subtraction, multiplication, and division, if they were equal before the operation, then after the operation, it's still equal. So if two things were equal before, then if I add the same term to both sides, it's still equal. Same thing with subtracting the same term from both sides, multiplying and dividing, provided that that thing you're dividing by is not zero. So these are just things that we already know instinctually when we're solving our equations. Our reflexive property, this is here to let us know that something is always equal to itself. So if we had to get rid of something, we know that how much that thing is. The symmetric property is so that we can go through and understand that just like when we look at math, 2 plus 2 is equal to 4. And if we switch it around, 4 is equal to 2 plus 2. It's important for us to know that we could switch around the order of our equation either way and it's still the same thing. Now, the transitive property is when you have two different equations that both mutually equal something in common. So these both equal B in some way. If A is equal to B and C is also equal to B, that means that A is also equal to C because they both equal the same mutual term. The substitution property, that's things that we've always come through when we solve our equations. We can always know that if these things are equal, then we can replace this wherever we see in our expression so that we can evaluate it to see if it's true. And then the distributive property, this is just important to know. If we got something that needs to be multiplied to an addition or a subtraction problem, then those products are still the same as what we had before when they were separate. We just have to be aware of what happens. That A gets multiplied to both B and C, and they're still going to be adding. Or times B and C, and they'll still be subtracting. Now, all of these are just properties of equality. These are when we use them for equations. But some of these properties come through when we're talking about congruence. Now, when we're talking about congruence, it's important to know we use the congruent symbol. So, when we look at the reflexive property, when we were looking at it with just equality, we just had something was equal to itself. We still have a similar concept, but this time it is an object, a figure is congruent to itself. Same thing with an angle is congruent to itself. We have to be aware these symbols here, the symbols of the shape as well as the congruent symbol, come up especially the more we're dealing with geometry. This also pops up with how the symmetric property looks as well as the transitive property. They're still the same properties we've met before, but instead of us using the equal sign, we use the congruent sign. And instead of us having no symbols for these objects, we keep the symbols for these objects, these shapes, these figures that we're dealing with. All right. let's jump into some work, folks. All right, jumping into our main words that we got to go through and talk about. We got to talk about what a definition is, a postulate, and a theorem. These are the things that we're going to use throughout our proofs, so pay attention. A definition is a precise description of a word used in geometry. All definitions can be written as a biconditional. Now remember, biconditionals, that's when we have that if and only if clause in the sentence. So a triangle is isosceles if and only if it has two congruent sides. This links up these two very closely. That means that if you have one bit of information, you have this other bit because they are intrinsically linked like that. Now, when we're dealing with a postulate is a statement that we assume to be true without needing any proof. Not everything that you're going to be using in a proof is a postulate, but there are some terms that we know, some postulates that we've worked with in the past. So there's exactly one straight line through any 2 points on a plane. If you drew 2 dots on your piece of paper, you can go through and connect them with a line. That's the whole point of a postulate. That's just something that we know it makes sense when you think about it. Now, a theorem is different from a postulate because a theorem can be proven to be true based on postulates or previously proven theorems. So that means that this required a little bit more work for us to accept that it is true. So the sum of the measures of a triangle is 180. That is a theorem that's backed up by other bits of evidence that you can get when you measure out a triangle. Finally, we have our main topic, a proof. A proof is using deductive reasoning to show that a conjecture is true. We've looked at a couple of different ones in assignments, like our reading assignments from over the weekend, but we have 3 types that you could mess with: 2-column proofs, paragraph proofs, or flowchart proofs. We're going to be mostly focused on 2-column proofs, but if you like these other 2 from looking at them from our reading assignments, you can go ahead and use them. So let's take a look at a proof together, people. A 2-column proof is like how we see here. It's formatted into 2 columns that are numbered with chronological steps. Now, these on this side, these are all called statements. They lead to your desired conclusion, what's at the very end of the proof. Then on the other side, we have our definitions that we use for them, our postulates, our theorems, and or properties that will pop up. These are things that we use called our reasons. So all of these are things that legitimize the steps that we're taking to solve this. Now, we have a little mix of algebra and geometry that we're going to be dealing with. So first, we always start our proof off by looking at the given bits of information. We're given this picture. This picture is of a line segment. I noticed that underneath the line segment, they also give me these 2 parts here. They say from D to E is 5x minus 3. And from E to F is 2x plus 9. They want us to prove that our x in this picture is equal to 4. So let's start off with the given information. They tell us that E is the midpoint of DF. So we put that out on our proof. That's given to us. Now, based off of this, we have to make another conjecture, another statement based off of this. So what does a midpoint do? A midpoint takes a line segment like where we're looking here with DF, and it cuts it right in half. So that means that from D to E, that's half of the line. From E to F, that's another half. If these guys are both halves, that means they're both equal to each other. And we know these guys are equal because that's what the definition of a midpoint is. That's what it tells us. Now, if DE is equal to EF, see how on line 3 we now have some algebra coming up with us? What we did is we used the information from our picture and we substituted this in so that we can make this equation so that we can start solving. So now that we're here, we got a couple steps that we get before we know that x is equal to 4. Sometimes in your proofs, you're going to be given a couple of reasons. You're going to be given a couple statements. So our next reason they gave us was that we're going to use the addition property. So looking through here, what term could I add? I can't add this, this, or this. Like these terms here, like 2x, 5x, 9, they're all positive. But I can add this -3 to the other side. If I add -3 to the other side, 5x is finally by itself. And then I got 2x plus 12. Now I need to get all my x's to one side. So I got to move this 2x over here to reduce this to 3x through subtraction. And now that I have my x's to one side, my constants to the other, to get rid of this 3, I just have to do the division property. Now, all this is stuff that we can go through and we can make sense of. This would be the same type of problem that you would have to go through to do if I gave it to you without a proof. But the only difference is you know what the answer is. It's what we're trying to prove. You're just going to have to work through the information to show me that this thing is true. So we got 2 proofs here that we got to go through and handle out. If you want to pause it and try it out, you can try it out and then come back. All right, hoping that you went through and paused it. If you did, good job. Let's go through and see what you could have found. Now, our first practice problem here has -2 parentheses 3x minus 4 is equal to 38. And they want us to prove that x is equal to -5. Things to be advised. You see how x is on the left? You can keep it on the left. You see how the 5's on the right? Keep it on the right. So that means that we're trying to move all our variables to the left, all our constant terms to the right. So use that to help you out. If you ever get caught up in a mess, you can always go through and switch it around using the symmetric property or the reflexive one. So starting off, we got our given statement. This is our equation that's given to us. Now I see that there's parentheses here, and I say that they're telling us that we're using the distributive property. That means that this left side here changes to -6x plus 8, and this side stays the same. Now I want to get my x by itself, so I got to move that 8 from this side to over here. Since we were adding, over here we would be subtracting. And then to get x finally by itself, we got this -6 next to it. That means that we got to divide it. So we didn't have that much of a mess to really deal with. Sometimes we will, sometimes we won't. We just got to take our time. Now our next property that we got going on here, well, not property, our next proof that they gave us here. They already gave us the equation, and then they gave us our reason. Just like before, we saw parentheses. We don't want to see those parentheses. So what we're going to do, we're going to distribute these. Now, we distributed these guys, and I notice on my next line, they filled in the statement for us. What's gone from over here that wasn't originally there? That -20, that's disappeared. That's a problem. We don't want that. Now, even though right now this seems like it could be a problem, I don't see my y over here to the left like I'm going to prove. We're going to eventually switch this around, so don't worry too much. Now, I went over and I brought this 6 over to the left side by adding it. Now, both of these sides here, I got to go through and handle with division. I see that I wanted to prove that y was equal to 2, not 2 was equal to y. So that means I can go through and switch this around with either the reflexive property or the symmetric property. Now, we're going to get into some higher level proofs when we come into our next lesson. I appreciate you coming by and watching this lesson. Y'all have a good night. See you later, dog.